Is it visible?
Yes, yes. Yeah.
Okay.
And the slides are
fine, and you are perfectly audible. Yeah, so it's a real pleasure for me to introduce Professor Atul Dixit from IIT Gandhinagar. He is a very good friend of mine, and he is so good to my students. They go, they do postdoc there, and they get good jobs. So for all of you, Atul is a really very active researcher, very prolific. He has a very good group in number theory at IIT Gandhinagar. And of course, needless to say that he is the winner of the Swarnajayanti scholarship this year. And he is already at such a young age, he has already so many students. He's editors of various number theory journals. And we are really privileged to have Professor Atul Dixit with us today. And I invite Atul to present his talk on Generalized Lambda series. So, Atul.
Yeah, good afternoon, everyone. Thank you very much, Kalyan, for the kind introduction. And I would like to thank all of the organizers, especially Kalyan, for inviting me to give a talk in this conference. I'll be talking on Generalized Lambda series, something that I have been working on for over 5 to 6 years. And I'll be talking on my work in these many years with my PhD students and postdocs. So Vivekananda Maji, Rahul Kumar, Rajat Gupta, and I inadvertently missed the name of Ashita Kesarwani, I'm sorry, in the abstract. So Ashita Somurup Banerjee and Shivaji Gupta. Okay, so let me start by looking at the definition of modular forms. A modular form of weight k on SL2Z is a function defined on the upper half plane which satisfies the following three properties. F is a holomorphic function on the upper half plane. Then for any ABCD integer matrix in SL2Z with determinant 1, if you have ABCD act on Z through Mobius transformation, we get AZ plus B over CZ plus D. So if we have F evaluated at AZ plus B over CZ plus D, then that gives us back F. And along with that, there is this factor CZ plus D to the power K, where K is the weight of the modular form. And the other condition that we need is F is holomorphic at infinity, because of which we have the Fourier expansion and whose coefficients have nice properties, arithmetic properties. Okay, so a classical example of a modular form is Eisenstein series, and I'm concentrating only on SL2Z. So EK of Z, where K is an even positive integer greater than 2. And here is the definition. I'm using the normalized Eisenstein series, normalized by means of this factor, where zeta of S is the Riemann zeta function. And here you see sigma sub K minus 1 of N. There is an arithmetic function I'll define in the next slide. So what are we interested in is this particular series, where sigma sub A of N is the sum of 8th powers of all divisors D of N. And A is the complex number, real part of Y is greater than 0, obviously required for conversions. And you can write this series in another form. I mean, that's easy to see. I'll also mention about it later. But if you concentrate on this series and we look at A equal to 2m plus 1, and I'm also going to let Y be minus 2 pi I Z. So because real part of Y is greater than 0, and if I let Y equal to minus 2 pi I Z, of course, it implies that Z is in the upper half plane. So with this, we know that when A is an odd positive integer, this series is nothing but essentially the Eisenstein series. I say essentially because it doesn't have that normalization factor and we don't have plus 1 in there, as you saw in the previous slide. But essentially, this is the Eisenstein series of weight 2m plus 2. Now, what if you take A equal to minus 2m minus 1? Then this particular series is the Eichler integral corresponding to the same Eisenstein series, E2m plus 2 of Z. What is an Eichler integral? So you take a modular form and you take its K minus first primitive. And then that is what you get, the Eichler integral of weight K or minus K. If I take A equal to 1, then this series, I mean, note that I have replaced Y by minus 2 pi I Z everywhere. However, in the rest of the talk, I'll keep it to e raised to minus ny itself. Okay, but when A is equal to plus 1, then this series is essentially the quasi-modular form E2, okay, the Eisenstein series of weight 2. And when A is equal to minus 1, this is what appears in the transformation for log of Dedekind eta function, which is a half integral weight modular form. Okay, now let me look at the general definition of a Lambert series. A Lambert series is a series of this form, summation a of n q raised to n over 1 minus q raised to n, where a of n is an arithmetic function and q is a complex number lying inside the unit disk. Then it is straightforward to see that if you put q as e raised to minus y here with real part of y greater than 0, so that mod q is less than 1, then this q to the n over 1 minus q to the power n just becomes 1 upon e raised to ny minus 1. And then this series, you write it in terms of, in this form where the coefficients are now the Dirichlet convolution of a with the function which is identically equal to 1 at all integers, all positive integers. Okay, how does one do it? Essentially 1 upon e raised to ny minus 1 can be written as a geometric series. You interchange the order of summation, and then inside you put m times, say the geometric series for e raised to minus ny over 1 minus e raised to minus ny is summation m equal to 1 to infinity e to the minus mny. That mn you put as a k, or that k you replace by n, and then you'll get back this. Okay. So what we saw on the previous slide was a special case of this particular Lambert series where a of n was n to the power a for a complex number a. Because when you have Dirichlet convolution of n to the power a with 1, what you get is sigma sub a of n. Okay. From here. Okay. Now let us look at all of the things that we discussed so far through just one particular formula. This is the famous formula of Ramanujan for odd zeta values. So if alpha, beta are positive numbers such that alpha times beta is equal to pi square. Actually, you can analytically continue this for real part of alpha greater than 0 and real part of beta greater than 0. But this is how it was stated initially. So if these alpha, beta satisfy the condition alpha, beta equal to pi square, then for any non-zero integer m, you have this beautiful formula involving the odd zeta values and the Lambert series that we have been talking about. This n to the power a was minus 2m minus 1. So on the left-hand side, you see stuff involving alpha. And on the right-hand side, in the first expression, you see exactly the same thing, except for a factor in the front, which is minus 1 to the power minus m. And then you have a finite sum involving the Bernoulli numbers. Why is this formula very important? We'll be seeing this very soon. However, a special case of this predates Ramanujan's work on this, which was due to Lerch. And it is when you have alpha and beta equal to pi, and when m is an odd. Of course, Lerch did not know of this general formula, but now that Lerch's formula is already there, one can actually deduce it as a special case of Ramanujan's. So what happens when you put alpha and beta equal to pi and you let m be equal to odd integer? So of course, minus 1 to the power minus m will give you a minus 1. And then alpha and beta both are pi. So if you take this expression on the left-hand side, you get just one zeta to m plus 1 and then one Lambert series, and which is equal to this particular finite sum. We'll talk more about this soon. There is a nice survey article written by Bruce Berendt and Armin Straub, where they explain the history of this formula and its implications as well as modern interpretations. So let me now explain some applications in which this modern interpretation of this formula would be evident. So the first one is that Ramanujan's formula encodes the transformation properties for Eisenstein series on SL to Z and their Eichler integrals. How do we see this? So let me go back. Let me see here, m is any non-zero integer. So if I take m to be a negative integer less than minus 1, then of course this particular thing is just 0. And when I have here, say m equal to minus 2, then what does the exponent become? It's 3. So n cube over e raised to 2n alpha minus 1. What is this becoming? I mean, there is no finite sum, right? So this is nothing but the transformation for Eisenstein series of weight 2m plus 2. Okay, like E4, E6, E8, all of them are coming from here when I take m to be a negative integer less than minus 1. I mean, here it is with alpha, beta greater than 0, or as I said, through analytic continuation, you have real alpha greater than 0, real beta greater than 0. So if you let alpha be, say, minus pi iz, I'm saying minus pi iz rather than minus 2 pi iz because there is already a 2 in here. So then you turn into the upper half plane. Instead of right half plane, you are into the upper half plane. And then that way you can very easily see that this is nothing but the transformation for the Eisenstein series Ek of z, where k is a even integer greater than 2. But there is more to this. If I take m to be a positive integer, then of course this thing remains. And then what I get is the transformation for Eichler integral corresponding to the Eisenstein series of weight E2m plus 2. If I take m equal to minus 1, what do I get here? The exponent becomes 1. And you know what this series is. It's essentially the E2, the quasi-modular form. And that is, why do we say quasi-modular form? Because it doesn't satisfy that modular transformation. Why? Because when m is equal to minus 1, there is one expression that remains, I mean, one term. And that basically is the obstruction to modularity. Now, one cannot, of course, put m equal to 0, and that's why one has to remove this, but the series itself makes sense when m is equal to 0. And so one starts with the series and then transforms it into this. You will see that we get essentially the transformation for the log of Dedekind eta function. I mean, the transformation eta of minus 1 by z is square root of minus 2iz eta of z. This is what we get. Okay, so all of this is encoded in this one particular formula. Another thing is that there has been a paper by computer scientists, Kirschenhofer and Prodinger, where they have used it in analysis of special data structures and algorithms. So basically, all these corollaries that I said, coming through Ramanujan's formula, they have used it to achieve certain distribution results on random variables related to these data structures that they call as tries. So theoretical computer science also has applications coming in from Ramanujan's formula. Again, as I said, Lerck's formula, which is given here, is a special case of Ramanujan's one. What is one thing which is straightforward from this formula? I mean, except for this pi to the 2m plus 1, all of this is a rational number. So the right-hand side is a rational number, a rational multiple of pi to the 2m plus 1. Pi is transcendental. So the right-hand side is transcendental. So at least one of zeta 2m plus 1 or this Lambert series has to be transcendental, is what we can get from here. This fact is explicitly given in the paper of Gun, Murthy, and Rath. So why is this a big deal? So basically, there has been a conjecture in transcendental number theory on odd zeta values saying that there cannot exist any polynomial in these n plus 1 variables over Q, such that when you put pi for x0, zeta of 3 for x1, and so on, then you get equal to 0. What does that mean? That means, let's say, for example, I take my I take only x0 and my n is equal to 1. Then I'm talking about p of pi comma zeta of 3 not equal to 0. There does not exist any polynomial p such that p of pi comma zeta of 3 is equal to 0. And what will that imply? That will imply that there exists no algebraic relation between pi and zeta of 3. In fact, even if I put just one variable here, that immediately implies that all of these zeta 2n plus 1 are transcendental. And more so, it also tells us that these odd zeta values are not algebraically related to each other. In fact, we know very little about arithmetic nature of odd zeta values. We only know that zeta of 3 is irrational, not even transcendental. We don't know about it. But zeta of 3 being irrational is a celebrated result of Aperi from 1979. And currently, the best result for the next odd zeta value to be irrational is due to Zudilin, which says that at least one of zeta of 5, zeta of 7, zeta of 9, and zeta of 11 must be irrational. But we don't know which one as of now. Now compare this with even zeta values. All of the even zeta values, zeta of 2m, they are rational multiples of pi to the 2m, hence transcendental. And that is due to this formula of Euler. We all know zeta of 2m is a rational multiple of pi to the power 2m. And because of this, we have them algebraically related to each other. right? Because zeta of 4 would be pi raised to 4 over 90. Zeta of 2 is pi square by 6. So zeta square of 2 will be pi raised to 4 over 36. So you can actually get it in terms of 2 over 5 times zeta square of 2. Similarly, you can have these relations. So all of them, all of the even zeta values are algebraically related to each other. We miss this thing narrowly. If I go back, then you can observe that here also is a zeta 2m plus 1, and here also there is a rational multiple of pi to the 2m plus 1. But there is this Lambert series, which is an obstruction towards getting this transcendental nature of zeta 2m plus 1, if at all it is transcendental. Okay. So Bruce Barron obtained a nice result, a very general result, which has as two corollaries Euler's formula for zeta 2m as well as Ramanujan's formula for zeta 2m plus 1. So both of them we can consider to be companions of each other, because both come from the same root identity. Let me also now discuss what we call as generalized Lambert series. So in generalized Lambert series, instead of having just exponential nz minus 1 or exponential ny minus 1, we are also taking n to the power capital N, where capital N is any natural number. On page 332 of Ramanujan's Lost Notebook, he does discuss such series, generalized Lambert series, where this arithmetic function here is of the form n to the power k. I mean, there are some conditions on k and n, but this is what is explicitly written on that page 332, except for there is no right-hand side. So we don't know whether he intended, whether he had some results and the pages went missing. We can never find it out probably. But he clearly had understood the importance of the generalized Lambert series. In fact, when n is equal to 2, we do see a result in Ramanujan's work where k is 0, for k equal to 0, because this is then infinite sum of partial theta functions. Okay, so Wigert was the first one. He was a Swedish mathematician. Wigert was the first mathematician who really considered this generalized Lambert series, but with arithmetic function identically equal to 1. Wigert was also the first mathematician who brought in Bessel functions in analytic number theory through Voronoi summation formula. And Hardy, this is a quote due to Hardy. Hardy says that Wigert was the first person to understand the importance of Bessel functions in analytic number theory. So there are several important works of Wigert, one of which is this work on generalized Lambert series. In fact, depending upon the parity of n, he has two separate results. If n is even, he has an exact transformation for this Lambert series, of course, with the arithmetic function being identically equal to 1. And if n is odd, then he has only an asymptotic formula. Further, this was pursued by Kanemitsu, Tanigama, and Yoshimoto in a series of papers, very nice papers. And but they looked at n even in most of their work. And when Vivekananda joined here with me in December of 2016, we decided to look at odd values of n, and try to see what we get, because one of the special cases would be when n is equal to 1, which gives us back the usual Lambert series. So then can we generalize Ramanujan's formula is what was the question in our mind. And here is the generalization. So n is an odd positive integer greater than or equal to 1. The condition which I had in Ramanujan's formula before was alpha beta equal to pi square. Now it is replaced by alpha times beta to the power capital N is pi raised to n plus 1. So when n is 1, of course, this is alpha beta equal to pi square. So for any non-zero integer m, you have this transformation. Let me explain this. It may look complicated in the beginning. So you have the odd zeta value here. Here also you have an odd zeta value. However, now you have two different odd zeta values which are related to each other. In case of Ramanujan's formula, there was n equal to 1. So both were the same. But now we can get relations between different odd zeta values through this particular Lambert series. And on the left-hand side, if you see the exponent of alpha here, it's 1. So you have only one Lambert series. Whereas the exponent of beta here is capital N. So you have n Lambert series on the right-hand side. And on the right-hand side, again, the last expression is nothing but a finite sum over Bernoulli numbers. So what happens when we put capital N equal to 1? Of course, this sum, this is easy to see. It just gives us back the left-hand side of Ramanujan's formula. However, on the right-hand side, you have j going from 0 to 0. Here you have e raised to pi I j over n. So this again becomes 1. Whether you have 2n to the power capital N or you have 2n to the power 1 by capital N, when n is equal to 1, it's the same. So you get back Ramanujan's result from here. And even though you see fractional powers of alpha and beta in here, if you put alpha equal to beta equal to pi, let's say, then the right-hand side becomes a rational multiple of pi still. And so you do have some results which come from the fact saying that at least some of these quantities, one out of these quantities is transcendental, that sort of result. Okay, we also worked further with even more general Lambert series that was considered by Kanemitsu, Tanigama, and Yoshimoto. And that is having an extra parameter here, A, something which is reminiscent of the parameter A in Hurwitz zeta function. And if you have guessed it, that is right, because Hurwitz zeta function plays a role in here as well. So when I put A equal to 1, this will give us back the previous series. Actually, Kanemitsu, Tanigama, and Yoshimoto considered without this minus 1. Sorry, there is a typo. But then we decided to work with this one and get a further generalization, which resulted in numerous corollaries, numerous important results as special cases. So this time, instead of zeta 2nm plus 1 linked with zeta 2m plus 1, it is linked with cosine 2 pi na over n to the power 2m plus 1, n equal to 1 to infinity. Of course, if you put a equal to 1, you get back zeta 2m plus 1. So I won't give the general result here because it will take some time to explain. However, I do want to point out that in the proof, there was one very interesting result in itself that was employed. So it was a new result that this particular series of integrals, see integrals consisting of elementary functions in their integrand, has a closed form evaluation. Here psi is the logarithmic derivative of gamma function. This integral has been evaluated, but when you see its evaluation, it is in terms of some non-elementary special functions. I mean, those which are not very well known. Okay, I just want to keep track of time. So, okay. So it involves, the integral itself is evaluated in terms of functions which are not so well known. However, when we sum that, the right-hand side is in terms of well-known special functions. The logarithmic derivative of gamma function is quite well known. Also, a moment's look will tell that one cannot interchange the order of summation and integration here, otherwise one gets a divergent integral. So how do we obtain this? This is through using a generalized Poisson summation formula due to Green and then evaluating a bunch of integrals and limits. So the proof is interesting in itself, but I'll skip this part. Let me come back to this series, which we can write equivalently in terms of the Lambert series corresponding to n to the power a, right? And now let a be any complex number. In general, this is conversion. But what we know is only when a is odd. And we know that this is essentially the Eisenstein series for positive odd integers. For negative odd integers, it is essentially the Eichler integral and so on. But what is absent in the literature, or what was absent in the literature, was how do these transform exactly? Explicit transformations were not available. People have done work on them. I mean, when a is an even integer, sorry, I forgot to say that. When a is an even integer, one has not been able to see explicit transformations in the literature. Guinan himself worked on summation sigma sub 2k of n e raised to minus ny for any k real, but such that k plus half is not an integer. If k plus half was an integer, 2k would have been an odd integer or positive integer, and for that, or odd negative integer, and for that, we already have information through Ramanujan's formula. So he takes k plus half not equal to an integer, and then he has a transformation for here, for this series, which is in terms of, so what people do is, there are two lines of approach. One approach is that you take this and you try to see where the modularity is obstructed. So you try to get this transformed into something which has on the other side the same series with y replaced by some constant over y. But then you are having an obstruction due to modularity in terms of either a extra integral, which can be a line integral or a principal value integral, or you have some other obstruction. Okay, so for example, on page 269 of the second notebook of Ramanujan, there is this beautiful result where now this is his terminology, so I have kept it constant. So n is complex, real part of n greater than 2. And you see exactly the stuff which was there in Ramanujan's formula before, provided there is this cosine, and there is this principal value integral. But if I take my n to be an even integer greater than 2, which is what we have in terms of Eisenstein series, right? Say n is 4, then k cube over e raised to alpha k minus 1 or so on. So when n is an even integer, let's say n is equal to 2 times L. This thing is 1, this thing is 1, this thing is 0, this completely vanishes, and you get the transformation for Eisenstein series. So here also Ramanujan was trying to transform this into itself with alpha replaced by beta, of course, as much as possible. And then what is left is this principal value integral, or in Winand's case, there is some complex integral. But there is another line of approach where you don't have any principal value integral or a line integral, but you have one series, meaning, let's say, if I concentrate on this series getting transformed into something where again y gets replaced by some constant over y. And this y getting replaced by some constant over y is equivalent to z going into minus 1 by z, the inversion. Because here this is in the right half plane, whereas z is in the upper half plane. So that's why y goes to 1 by y in this case. But you want this to transform into something which has some constant over y in the exponential, but then you don't have the same arithmetic function here, or you don't have the same series. You have something different. So we followed the second approach, and today I will be presenting some results through this approach. So I'll just point out that there are some results due to Bettin and Conray also for the same series with general A complex. But again, he has it in terms of, they have it in terms of line integrals. And so an explicit transformation, which is what we mean by just a bunch of residues, plus again the explicit series without any obstruction, but then the series now doesn't look similar to previous. Like here you have the same series, just alpha is replaced by beta. It won't be the case in our case, but there won't be any principal value integral. So let me mention that general result. So this is joint with Ashita Kesarwani and Rahul Kumar. So just a few days back, this paper has been provisionally accepted for publication in Research in the Mathematical Sciences. However, we don't have a firm yes. I mean, so I say provisional acceptance. So we have, again, the real part of y greater than 0. Any complex A says that real A is greater than minus 1. And then this series, which is the Lambert series associated with n to the power A, gets transformed into this series. Now this transformation looks somewhat complicated, but the remainder of the lecture will be based on telling everybody that this is indeed a useful transformation. So what is this 1f2 in here? 1f2, so before even I discuss this 1f2, I just wanted to make sure that I explain what I said previously, that here is a y in the exponent. And on the right-hand side, everywhere, you see 1 by y. There is a 1 by y here, 1 upon y, then 1 by y squared, and then 1 by y and 1 by y. So that is what we intended. And there is a bunch of residual terms that comes out. Okay. So what one can, okay, let me explain first what 1f2 means. So in general, this PFQ, generalized hypergeometric series, is defined in this way. So you have these which are called as shifted factorials, and they can be written as quotients of gamma functions. They're called shifted factorials because if you put a equal to 1, this becomes a factorial, n factorial. So you have P shifted factorials in the top, Q shifted factorials in the bottom, and then Z raised to n over n factorial. With regards to convergence of this series, if P is less than Q, which is what we have in our case, 1f2, then it converges absolutely for all Z. In fact, for P less than or equal to Q. But if P is equal to Q plus 1, like in the case of Gaussian hypergeometric function, the convergence of this series is only for mod Z less than 1. And it diverges for any non-zero Z with P greater than Q plus 1 if the series does not terminate. Okay, with this, let me move also to what we call as master identity, where on the left-hand side, you see exactly the same thing, but on the right-hand side, you have a more complicated thing, but the condition is more general. Initially, I had real part of A greater than -1. Now I can move however much I want into the left half plane. And how does one go about this? So one goes about this in this way. This function, first of all, is nothing but what I had in terms of that 1f2 and all in the previous slide. So I have that thing. I look at its asymptotic expansion as n tends to infinity. And from that asymptotic expansion, I subtract finitely many terms. Say I subtract this m plus 1 many terms, because I have minus of this a sub m, which is a finite sum consisting of m plus 1 terms. So I add and subtract that. With real part of A greater than -1, it is still a valid identity. Now that subtracted part is here. The added part I take outside and I sum with the help of this sigma sub A of n. It becomes a product of zeta functions, right? Everybody knows about this. Still real part of A greater than -1. So this is a valid identity. But then I notice that, okay, because I have subtracted m plus 1 many terms from the asymptotic expansion of this as n tends to infinity, now this series converges in a much wider region, real part of A greater than -2m -3. And the rest of the expressions here are also analytic. Because this series is actually uniformly convergent in real part of A greater than -2m -3, any compact subset of in A complex plane, this represents an analytic function. Everything else is also analytic, except for, say, when A is 0 here, or A is -1 here, that sort of thing. That then implies that I can use this result to get analytic continuation of my previous result. And here M is taking a value for M is in our hands, right? So however much I want to go into the left half plane, I can go. Of course, I cannot let M tend to infinity because otherwise this series diverges. However, if I want to have A equal to say -50, I can take M appropriately and then do it. So for any A, we can actually do this. Just that I'll have to subtract many, many more terms if I have A further into the left half plane. Okay, so this looks complicated in the first glance. However, we call this as a master identity because this has many, many important results as corollaries. First of all, when we take A to be any negative integer, positive or negative, we get Ramanujan's formula as a special case. But we can also now put A to be any complex number, right, satisfying this. So in particular, if you put A to be any even integer, again, positive or negative, then we are able to get transformation, which is what I'll discuss here. But before I do that, there is this general, some function of which we don't have much idea. So as I said, this is essentially that 1f2 minus something that I had on the previous slide. But it's in general, when I put mu instead of half or w instead of 0, this is a generalized modified Bessel function, which is defined in this way. There are some restrictions that one has to look at. And when w is 0, it reduces to a certain generalization of modified Bessel functions, which was given by Koshlyakov. And when we put mu equal to minus nu, then we get k Bessel function again, essentially, this times k Bessel function. Okay, so here is the result when we have A to be a positive even integer. so which was not known before. So what happens is that on the left-hand side, of course, we know this will be the series. What happens on the right-hand side is this one. And this, what are these functions, SHI and CHI? So they are essentially anti-derivatives of sine hyperbolic z over z and cos hyperbolic z over z. So essentially, these are their definitions. So SHI is the hyperbolic sine integral, which is defined in this way. CHI is the corresponding one, but it has this -1 here and then gamma plus log z, where gamma is Euler's constant. Okay, but one does get again into something which has sigma 2m of n, but then this one. And this is also natural. Now I'll talk about the combination here of these hyperbolic functions and hyperbolic sine and cosine integrals. In what way is it natural? So here's the thing. This is the series that appeared on the left-hand side on the previous slide. Later on, we'll also be looking at a equal to -2m or a equal to 0, which is nothing but d of n, right? Sigma 0 of n is d of n. So we'll show that this get transformed in general into this series. Now, when m is a negative integer or 0, this drops out. And so you have only this. But why is it natural is because of the fact that if you do not have SHI and CHI, so just sine hyperbolic minus cos hyperbolic, and instead of 2m, you have 2m plus 1, then what does it become? This is what we get in terms of in the Eisenstein series and all, right? In modular transformations, there is always an odd integer a, and there is essentially a difference of hyperbolic functions because that difference is nothing but this exponential. Now, when you replace that odd a by even a, you still have sine hyperbolic and cos hyperbolic as in here, exactly with the same arguments, 4 pi square n by y here also. But along with sine hyperbolic, you have to put a hyperbolic sine integral. Along with cosine hyperbolic, one has to put a cosine hyperbolic integral. Okay, so these are explicit transformations. I mean, I have not listed these because of lack of time. This I will talk about, but this is the one that I have not listed. However, I have given an equivalent form of it. So let us look back at Ramanujan's formula. So here was odd zeta value, and here was this Lambert series corresponding to n to the power -2m minus 1. What if I have here zeta 2m and here n to the power -2m? Does this again transform into something similar? The answer is no. What it transforms into is this. Here, that a is -2m is the case being considered. So I have exactly the same thing. But on the right-hand side, it doesn't give me back this Lambert series. Instead, it gives me this particular infinite sum over this digamma functions, something which are very important functions due to Zagier. So Don Zagier has worked on something he calls as Herglotz functions. So these are higher Herglotz functions because they have this n to the power some number which is greater than 1. But this is a companion to Ramanujan's formula. Why do I say it's a companion to Ramanujan's formula? The form is somewhat similar. I mean, instead of 2m plus 1 and 2m plus 1 in here, you have 2m and 2m. And instead of alpha to the -m, there is alpha to the -m minus half, beta to the -m minus half. On the right-hand side, you have this beta 2k, so essentially zeta 2k. So an even zeta times odd zeta value. Whereas here you had just even zeta values. Okay, so there are some transformations in the literature that one should be looking at for periodic zeta function, periodic functions, or periodic zeta functions one would call. I'll very briefly say, because when we encountered our formula and then we also encountered this particular result due to Bradley, we were first afraid that he already has our result because there is this 2m, there is this -2m, and in a more general sense, because he has a periodic function. But you cannot put here g identically equal to 1 because here g is an odd character or odd periodic function, whereas identically one function is an even function. So when you have 2m you cannot put G of n identically equal to 1. So our result is not covered in there. And when you have 2m plus 1, there you can put G identically equal to 1. So this is nothing but Ramanujan's form, a generalization, a different generalization of Ramanujan's result. Okay. This is due to Bradley, and there have been some other results due to Bruce Berndt, Katayama, and many others. Okay, now I come to another interesting aspect of certain transformations and some of my recent work. This formula is due to Wigert. Wigert wrote a paper in Acta Mathematica in 1916, which has been referred to many, many times. However, this formula itself has not received that much attention, even though it is really important, as we shall see. This left-hand side is nothing but Lambert series associated with the identically one function. You can also write it in terms of summation d of n e raised to minus ny, right? This readily implies this result, the asymptotic expansion for summation d of n e raised to minus ny. This is there in Titchmarsh's book, and many, many papers we'll see. People derive this using residue integration, residue calculus. So you start this, use Perron's formula, you write it in terms of contour integral, you shift the line and get the residues and everything. However, this is a trivial consequence of the result in here, and wherein you not only get you not only recover this formula, you actually get it, like if you put an asymptotic sign in here, you can get an exact, complete asymptotic expansion as y tends to 0, trivially from here. That's why I say this is an important result of Wigert. Now, why is this result, like previous result has been employed in the theory of zeta function a lot. So to do that, let me introduce first the moments of the Riemann zeta function. These are certain very important objects. So the 2kth moment of the Riemann zeta function is nothing but integral from 0 to t mod zeta half plus it to the power 2k dt. So integrate on the critical line. For a positive real number k, it is believed that when you let t tends to infinity, this moment is asymptotic to some constant depending on k times t times k square power of log t. Even though there are models in random matrix theory coming from physics where people get a lot of evidences for this particular conjecture, as far as the proving itself, proving that is concerned, there have been only 2 cases that have been wherein we have been able to show that this is what we have. That is for k equal to 1 and k equal to 2. So k equal to 1, this is due to Hardy and Littlewood. For k equal to 2, this is due to Ingham. Now, instead of having this particular moment studied, there is a corresponding alternative moment that people study. There is a smoothly weighted moment. See, one cannot put here infinity, otherwise this will diverge. This integral will diverge. So if I want to put an infinity in here, then I'll have to put some exponential dampening factor in here. So that's what is evident in here. We put e raised to minus delta t, where delta is greater than 0, and then we have convergence. We can go up to infinity. Some people study these moments as compared to the previous one, and there are lots of connections between the two. If you know asymptotic expansion for this one, you can easily get, as delta tends to 0, you can easily get the asymptotic expansion for the previous one as t tends to infinity. So either one, people have been studying for many, many years. So now, using the asymptotic result of Wigert that I showed you, meaning, let me go back again, this one, which was a trivial consequence of this result. Atkinson, F.V. Atkinson, he found a simple proof of a result of Kober. Kober's result was a complete or an asymptotic expansion for this smoothly weighted moment as delta tends to 0. Now, this was devised using that asymptotic. But if one gets the full asymptotic expansion through that original result of Wigert, then one can actually get the complete asymptotic expansion up to infinity. Of course, it will be divergent, but still one will get the full asymptotic expansion and with effectively computable constants Cn. Okay, now here is something really recent that I would like to talk about, and that is, I think I have about 15 minutes, Kalyan?
Okay. Yes.
Okay. Okay, so I would like to talk about my recent work with Shomurup Banerjee and Shivaji Gupta, where we have found an exact transformation for this Lambert series corresponding to log of n. So we just submitted this paper for publication a few days back. Something like this has not been available in the literature before. If I go back to this connection between this A of n and then the Dirichlet convolution, when you write this in this form, see, people have it for a number of functions. Like if you put here instead of A of n, a von Mangold function, lambda of n, then 1 star lambda is log. But for log itself, there is no result available. So, but this is, I'll explain a beautiful consequence of that result that we are able to get. But let me say that one can obtain exact transformation for this, wherein y goes to 1 by y or some constant over y. So modular behavior, of course, without having the same thing back. One cannot get a modular form with this log n over e raised to n minus 1, but the same series, it doesn't turn up, but something which has 1 upon y or some constant over y turning up. Okay, first of all, if I put a of n equal to log n, what is this going to become? So I have 1 star log of n, which is nothing but log of product of all divisors of n. And what is the product of all divisors d of n? This is n to the power dn over 2. This is, for example, an exercise problem in Apostle. So we are getting now this series which has log n. So previously people had d of n e raised to n minus ny, which was very much useful in the theory of Riemann zeta function. Now you have summation d of n log n e raised to minus ny. But what does this transform to? So before I explain that, let me go over some work of Christopher Deninger. So he wrote a paper in Krella, which was quite influential. He studied comprehensively a function he called R, which is a function from positive reals to reals, which is uniquely defined by means of this difference equation. R of x plus 1 minus R of x is log square x, with R at 1 being this initial condition. And one can immediately see that this is an analog of gamma function, because what is the gamma function or log of gamma function? Log gamma satisfies this difference equation, right? Because log gamma x plus 1 minus log gamma x is nothing but log of gamma x plus 1 over gamma x, which is log x. With initial condition f of 1 is equal to 0. So I just want to make one comment that there has been a previous work of Professor Kalyan and Professor Kanemitsu, where they actually study such difference equations. I mean, this is called as Dufresnoy-Piso uniqueness theorem. So they have employed that in their study. The paper is the modular relation and the digamma function. So this one is also defined using the difference equation. And Deninger goes at length studying various interesting properties of this function R. So R is at the same level as log gamma x, right? So recently there has been a paper by Languesco and Righi where they call exponential of R of x as the Ramanujan Deninger gamma function. Why Ramanujan? Why not just Deninger? It's because in his notebooks, Ramanujan did work with the logarithmic derivative of this function. So now it is known as Ramanujan Deninger gamma function. Okay, so here is our explicit transformation for this logarithm, the Lambert series associated with log. So let psi1 of z denote the logarithmic derivative of the Ramanujan Deninger gamma function. There are a bunch of residual terms. Then there is this series which occurred in Wiggert's formula also, right? And then there is this new series involving the logarithmic derivative of the Ramanujan Deninger gamma function. Okay, this y over 4n comes very naturally and is required for convergence. So while I won't be able to go into the proof of this, I do want to say what all one gets with the help of that and where is this coming from. So again, it comes back to something that I introduced in the beginning. There was no means of having a log n up to now because the Lambert series corresponding to n to the power a, which is essentially this series, right? You can write this as Lambert series associated with n to the power a. There was no transformation available for it for any complex a. Sorry. Now there is. This one in my paper with Ashita and Rahul, we have this for any complex a. So the moment we have this and the moment we have uniform convergence of the series, we can now differentiate both sides with respect to a, let a be equal to 0. And if we do that, then after a lot of intricate calculations, we actually get the previous result. Another thing is that with the help of the previous result, we are able to get the complete asymptotic expansion of this Lambert series associated to log as y tends to 0. And that is useful in the zeta function theory because it gives us a Kober type asymptotic expansion for this smoothly weighted moment of zeta half minus it times zeta dash of half plus it as delta tends to 0. Okay, so let me say in my last slide that there have been results due to Ingham which have been applied by Gonek to get asymptotic for this particular integral. Note that it's not the smoothly weighted one, it is the one with t. And there is no exponential dampening factor in here. But for any mu or nu, which is a natural number or 0, of course, when you put mu and nu both has 0, this gives you the second moment of the Riemann zeta function, asymptotic for that. But if you have any mu or nu to be n union 0, this is the asymptotic that one can get from certain results of Ingham. This has been further extended by Caroline Ternage-Betterbau, and she has shown that here is the main term and here is the error term. And more information that one we have here. And so if I put here mu is equal to 1 and nu is equal to 0, then our previous, the one that I had on the previous slide, that was the smoothly weighted version. But we have this asymptotic for this particular moment, which is minus t over 2 log square t. But what is in addition available in our work is that not only the leading term, the full asymptotic expansion one can get with effectively computable constants. So unfortunately, I don't have time to go over that. So with this, I will stop. Thank you.
Great. So any questions from the audience here in the seminar? Yeah, I think it was quite expensive. I mean, the amount of work that you are doing in Lambert series, it looks, I know you have got very good students. Doesn't seem like there is any question in the seminar room, so I can ask the online audience if you have any questions. You can unmute and ask if you have any questions. Yes, you can contact, of course, Atul. He is, one person who will be always eager to respond to you in your queries. Thanks a lot, Atul. It's a fantastic lecture, and
Thank you, Kalyan. Thank you.
See you here.